And finally, we talk about an approach that is really popular in the industry, and especially in the process industry, so in the chemical industry, which is a principal component analysis. Principal component analysis is yet another way to generate features out of a signal and then symptoms. And the interesting thing is that the principal component analysis is a way to filter out non-important things from your observations and get features that are the one that mostly describe the behavior of your system, of your signal. And everything else that is due to noise or that is not important is filtered out. So there is some big dimensionality reduction in the way that PCA is going from observations to features. And then from these features, it generates symptoms. In particular, it generates two types of statistics, that is random variables for which we can implement a symptom evaluation using a probabilistic change detection approach. In the previous lectures, we have seen as examples the t-student and the chi-squared variables. We call them random variables, but in other settings, especially where PCA is done, they call them statistics. So the main idea of the PCA is to start with an assumption. So the assumption is that we have a huge set of measurements. So the dimensionality of this set of measurements is too high to just look at them as they are. And also we assume that the process generating this measurement is slow. So we are always in stationary conditions. As we have this huge set of measurements, we want to reduce the dimensionality of data. And to understand how this is done, let us make a visual example. So let us assume we are just in 2 dimensions. And similarly to the example we have shown for the Mahalanobis distance definition, well, if you look at data that is normal, then it is going to be distributed as an ellipse. So if you take a lot of samples, nominally they are distributed like this. In practice, it means that these two variables are not independent. There is some correlation, and this is expressed by this main axis of our ellipse. So this is the direction over which they are mainly correlated, and the other direction is this one, so the minor axis of the ellipse. So a way to reduce the dimensionality of these is to consider only the variation along these axes, because this is the one where most interesting things are happening. So especially if this ellipse is really, really squeezed, and so variation over this dimension is really small, well, it is somewhat negligible. So we may just be interested on where we are along these axes. So can we reduce the dimensionality of data from the actual 2, so we have these 2 like axes, to 1? Yes, we can. And we decide to describe this variation as coordinates along this direction, where most of the changes are happening. So the idea would be then to project every data point on these axes. So if you do for all these, you see that your data points starts to become like this. They are concentrated along here where most of the samples are, and then few of them are farther away. The idea of the PCA is actually to do that, to identify directions of maximum variance of the data where things that are interesting are happening, to ignore what is happening on other directions that are perpendicular to that. And look at just the projections of data over directions of maximum variance. Once you have that, instead of having vectors of data, in this example at least, you have scalars. And on these green points that represent your data projected here, you can then implement some change detection algorithm. And this is the idea of PCA. And PCA is providing all these steps. It's providing a way of reducing dimensionality of data by generating the features, the samples around this direction, and then implement specific change detection algorithms. Let us see how. From a mathematical point of view, we assume to start with n normalized samples for each of the m sensors. So we have n samples coming from m sensors. So we have a data set that is a matrix, not a vector. And every column is normalized, which means that it should have zero mean and unitary variance. If it is not the case, you need to normalize your data, which means you need to subtract the mean and then divide by the variance of each vector for every sensor. Anyway, once you have done that, you end up with Z1, Z2, and Zn. So these are the samples out of your M sensors that are put together into this matrix, the data set, that has dimension M by N. Then the second step is to compute the covariance matrix, C. Indeed, as we said, we are looking at a way to describe our data through the covariance, and especially through the directions where covariance is maximized. So we compute the empirical covariance, which is computed this way. So Z transpose Z divided by N minus 1, similarly to the way we compute the empirical variance. And then it comes the transformation that is leading to finding those directions of maximum variance. And in particular, we compute the singular value decomposition here. And as a result, you get a diagonal matrix lambda, and these matrices, these orthogonal matrices P. The matrix lambda contains on its diagonal the singular values. But P, the orthogonal matrix P, has on its columns the singular vectors. The singular vectors are the ones that are describing the directions over which data is varying. So if you do the transformation of these data in the matrix P, you get the two vectors that correspond to this axis and this axis. And this axis has a singular value attached to that is the biggest, and this one has the singular value that is the smallest. So you can imagine how we are going to proceed. We are going to look at only the most important components of lambda. Because if we assume that lambda is ordered such that you start with the biggest lambda and you go to the smallest lambda across the diagonal, well, then you can split lambda into two blocks where you have the biggest, which are called the principal components, and the smallest, which are called the residual components. How do we define what is big and what is small? Well, it is up to us. So some way we generate a threshold. One way could be to consider the singular components that make up, let's say, 90% of the energy of the signals in your dataset. This could be an option. Anyway, once you have the big singular values, the principal components, You split also your matrix P into two blocks, one of the singular vectors corresponding to the principal components and the one corresponding to the residual. So let us assume that we keep L components, 10P principal components is a matrix with dimension M by L. Okay. So once we split our transform data, we have just gone through one part of the job, which is to generate features. Now we need to generate symptoms and evaluate them. And here is the part that is a bit more complex from a mathematical point of view. So there are several approaches, and I am talking about two. One approach is to generate a symptom that is based on the squared prediction error. And this statistic based on the square prediction error is also called the Q statistics. The other symptom that I can generate is based on the t-squared variable, which is also called the Hotelling statistic. Before we move on, you may ask yourself what we mean by squared prediction error. So look at this. What we have is Z transpose that multiplies P res, so the residual principal vectors. So you know that if you take a vector and you multiply it by an orthogonal matrix, that this orthogonal matrix is representing then directions. And by doing this multiplication, you are projecting Z over these directions. So, but these are the residual directions. So what does it mean? Let's go back to the figure. So in this figure, I shown you what happens when I project over the principal direction. So these green points would be equal to Z transpose that multiplies the matrix P, PC. So the matrix with the principal directions. But actually, we can also project on this other. You can also think, I don't know which color to use, but let us assume that you project all these data points on this direction. This would be equivalent to this other product, Z transposed that multiplies P residual. So if you consider keeping only the principal components, then you are describing your data only as the projection over this. Everything that is happening on the other directions is considered noise. So what is the value of this noise? It is equal to this, Z projected on the residual, on the small direction. So we call it residual because it is also true that if you take your original signal minus what you can reconstruct by projecting on the main direction, this is what is left. So this is the residual. So this noise, you call it the residual. And the idea of the SPE of this statistic here is indeed to look at the energy of this residual. The energy, because you take actually this product here, you see, you have Z transpose that multiplies this matrix, and then you have this matrix transpose that multiplies Z, but this is the transpose of the first one. So basically you're computing the square, so the energy of this signal. So what's the point of that? Well, to understand this, you need to consider one important thing. The important thing is that when you compute the principal directions, you are taking data in a nominal condition. That is, you take this cloud of points in nominal condition, and you get as an output of this your principal components, so the biggest singular values and the biggest singular vectors, the directions. But this is something that you do, let's say, at the beginning, when you tune the PCA to your system. So you take healthy data, you compute them. But then, when you want to detect a fault, then you are taking a new sample that is from operating conditions. So this new sample, for instance, can be here. So this is now the sample, the data that you use for implementing the test we have just introduced. So when you compute the Q statistic or the t-square statistic, you are computing on new samples that you are getting in operating conditions. And these are the ones that can either be normal, so be mainly concentrated along this direction, or abnormal, as this example. This is abnormal because if I project it back to the residual direction, well, the projection is quite big. So for this point here, the SPE is going to be big. But anyway, I repeat it once more just to be sure it is clear. P residual, P principal component, lambda principal components, you compute them once, let's say, offline with nominal data. Then SPE and t-squared, these two statistics, are computed on the sets of data that you have live, online. So the idea, anyway, for these statistics, you want it to be small, and indeed you compared it to a threshold. And for a t-squared statistic also, you can introduce another threshold such that if your t-squared is less than this, you have no fault. If SPE is less than this, you have no fault. So the difference between these two statistics is how you compute them and how you compute the threshold. So the Q statistics, the SPE is based on the residual, but the hoteling, you see, is based on the principal component, because you take your data and you project it on the principal component directions. You normalize it by the amplitude of the principal components. So this is some way similar to what the Mahalanobis distance is doing. You don't have the square root, okay? And the normalization factor is this matrix product here. But apart from that, it's basically the same thing that the Mahalanobis distance is doing. Regarding the way to compute the threshold, well, the formulas are a little bit complex. At least for the hoteling statistic, they are not so bad, because you have this expression where you have L, the number of principal components, and the number of samples. And then you have here F alpha. You remember the F test we had in the previous lecture? Okay. So this is the threshold of the F test for a significance level equal to alpha, in the case that you have L and N minus L degrees of freedom. So this is something that is not so complex to compute. For the SPE, well, the formula is a little bit involved. So you have a combination of these terms where you have theta 1, 2, and 3 that you obtain by these formulas. This is a summation of the singular values in the residual, because you see you start from L plus 1 to the I power. So theta I, you have a 1 I power here until to the last one. Then you have this H0 that is computed like this way. Anyway, if you want some details about how to compute these, you can look up these two papers that are explaining the approach in quite a simple and complete way. Anyway, These thresholds are based only on quantities that you compute once, because these singular values, you compute it once on a data set expressing the healthy behavior of your system. And these normalizing factor also, you can compute them once for all. So the only thing that you need to do online is take the last sample of data, normalize it, and compute these statistics and compare to the thresholds. Okay, so today we presented a brief description of some signal-based methods. There are many more that we are not covering, and we are also not covering any method that is using machine learning approaches. So we just briefly mentioned in some of the previous lecture, for instance, support vector machines, but we are not covering. But you can easily imagine that if you can generate features using any of the approaches we have seen today, then you can build an SVM classifier for these features. So this is something that unfortunately we are not covering. We are not going too much further into the details of signal-based approaches because of the drawbacks that we mentioned, that they are especially important for dynamical systems that are operating over transients. So as control systems engineers, we are really interested in this kind of behavior, so we will focus our attention more on model-based approaches that we're going to cover in the next lectures, and they allow to do a diagnosis in any condition, transient or stationary.